So welcome everyone to another OCP Tap call. This is call number 130, and we have today Shalomi Dolev. I will hand it to Ken Bierman to introduce our speaker. So Ken.
Okay, well, it's a great honor and pleasure to introduce my friend Shlomi Dolev, who is one of the real luminaries in distributed computing and, of course, this area, self-stabilization, and in general in the theory of computing. So I don't know if people know the story of self-stabilization, but it started very far back, actually. I think it was 1973 when Edsger Dijkstra showed a small self-stabilizing protocol and said, we really ought to think about this style of protocol. And it was completely ignored. And then self-stabilization was rediscovered almost 15 years later. Leslie Lamport was giving an invited talk at PODSI, and he said that he thought that one of the most important pieces of work and ideas in all of distributed computing had been completely ignored, which was true. And he said it was self-stabilization, and he introduced a small improvement on Dijkstra's original protocol, and Leslie's talk was forgotten. And then Shlomi came in as a student. It was his master's work. And he wrote the paper that has now become the second most famous paper in self-stabilization. It was on self-stabilization with atomic registers, and it really got a lot of attention. The area took off. Shlomi by now has written, I'm sure, hundreds of papers and books on self-stabilization. And he has created companies which use ideas from self-stabilization in other settings, blockchains recently, and time, which of course is the interest here, and in systems of various kinds. We don't yet have the terminator, but when someone builds the terminator, they will use self-stabilization algorithms. That's the idea, right? It pulls itself together when Arnold Schwarzenegger smashes it into pieces. So Shlomi is a remarkable guy, and he's not only a researcher. He's also been quite a leader. He created one of Israel's top computer science departments and was the chair for many years. He then became the dean, and he has gone on to be on a tremendous number of committees. He's gotten recognition and prizes both for his research and for his leadership in different kinds of contexts. He started two companies and explored commercial spin-offs of this kind of work. So it is really a pleasure to welcome him and hand over the speaking role to Shlomi Dolev.
Thank you very much, Ken. I appreciate your introduction. Yeah, our friendship should go for many more years, both of us. So let me tell you a little bit about self-stabilization, which I think is a marvelous idea and concept. I will tell you about time, but first let's look at the Dijkstra first algorithm, which is a very nice way to start and understand the area. So if you have a ring of processors, and one of them is a root, the rest are the same, and the task of them is just to have some kind of mutual exclusion to get to a printer, then you can have a very nice algorithm that, of course, if all of them start in an initial state where all of them are, say, green, then the root can change its color to purple. And then when it's done printing, and then the next one on the right will change its color to purple after E is printing, and so on. So this will be a round robin algorithm that is simple, maybe look like a token ring. But what happened if something is corrupted? And what do we mean by corrupted? Well, each of the participants has a program, and the program has variables, and the state of the processor is the content of these variables. So you can look at an algorithm where there is one variable, which is x, and for this special processor P1, it's x1, and the rest is xi. And this special processor P1 is breaking the symmetry whenever it sees that the last variable is the same as its variable. You just change the color. So it's using x1 plus 1, mode n plus 1, and assign a new color to its state. The rest, just look at the previous one clockwise, and if they are different, copy. Of course, when they copy, they let the next in the direction to print, and then they copy. So once you see that something is enabled, either you are in line number 2 or line number 5, you are able to print. And then when you are done, you executed the assignment of line 03 or line 06. So what is special in this algorithm? Well, we need that exactly one processor will print, and everyone will print infinitely many times. And we want to reach a safe configuration after these X's have some, arbitrary value that we don't know what happened. We don't care what happened, because if we care, we have to just consider every scenario by itself, and maybe we'll forget one of the scenarios. Better forget about what happened that brought us to arbitrary configuration, and just concentrate on how you regain consistency and achieve your goal. So this is an example that is using some mode. So in our case, if we use mode n plus 1, as the number of colors become n plus 1 colors from 0 to n, then there are nice properties. For instance, if you take a configuration, arbitrary configuration, then there is at least one color or one state that is missing, because you have only n processors and you have n plus 1 possible states. So at least one is not existing. And this is a key observation, because if the root that can introduce, the only one that can introduce new states, if this root introduces this missing value, then everybody should copy this value from the root, and the root eventually will receive it before it changes to the next state. And when it does so, the system is in a safe configuration where all clocks are the same, or all the values are the same. It's not clockiest. So just, is the observation that there is a missing value, and that the special processor change its state infinitely often. Both those observation makes the convergence, and then the safety forever happening, this magical achievement. So why this special processor change the value infinitely often? Assume that it doesn't, then every other will copy its value, especially the neighbor to the right will copy its value, and this value is not changed. And then the second to the leader also copies, and so on. This propagate until the reader must read the state it is now in. And then by its program, it changes state. So the state of the leader is changed infinitely often, and eventually it reaches the missing one. If it reaching the missing one, the system in somehow is reset, but it's not, it's not explicit, it's implicit reset. We don't know when, but this will, as an outside observer, you are sure that this will happen. And this is very relaxing. You don't care what will happen. Eventually, the system will converge to nice mutual exclusion execution. So now let's look at the decadal clock case after we know what is self-stabilization about from Dijkstra first algorithm. And we just start with a very simple case where the clock value is unbounded, and then we go on and see how to bound the clock value. And then we also consider what happened if some of the participants do not respect the program, which means that they are Byzantine or adversarial. And this is something to combine recovery in face of some other properties, some other assumptions. So let's look at the case of unbounded clock synchronization. We assume for now that there is a global pulse. And what we are really interested in is that the value of the clocks will be identical. And once they are identical, they should be incremented infinitely often, simultaneously, and keep being synchronized forever. So here is a very simple algorithm, unbounded version, that will be as an introduction for the bounded one. And what each participant is doing, we think about general communication graph. And each one we just look for a neighbor with a maximal clock, including itself, and then increment the max found by 1. And this, of course, very simple, and you can imagine that if you start with arbitrary configuration with some values of clocks, the one that is the biggest will be just incremented every pulse by 1, and its neighbors will join this max because they choose the neighbor with a max clock value and be in sync with itself. And this leader will eventually, concord the entire system after d pulses, where d is the diameter of the system. So this is very easy. You just have a common plots, and eventually you have, no matter what state you start with, you have very fast all the clocks in sync and continue to be incremented by 1 in every pulse. However, we really don't like unbounded variables in self-stabilization, because while we look at the algorithm, any algorithm, and you say 2 to the 64, it's infinite, we don't care, until you increment to this value, it will take forever. This is not correct in self-stabilization, because we can start in any value, especially what happened if this value is some kind of a corrupted value that get to all ones by a single transient fault that we don't know what is the source of this fault, but this is happened. You don't ever want to be stuck. You want really to recover. So we must define what will happen if the value is already in the upper bound, because we don't have a system with unbounded number of bits. So let's do modulo. This seems like a good idea. Let's do, instead of just max, have max plus 1 mod n plus 1 d plus 1. And this seems like why this value, I will tell you in a minute. So m is this value. Now the increment mode this max value. And let's see what happens then. So let's have an example. So this is a system. We have P1, P2, and P3. This is a network. And m is, by our formula, is 9. Now, there is another representation that we can look at the clock values. Here the clock values are 1, 3, and 8 to P1, P2, and P3, respectively. But we can put them on the clock just to make another observation of what's happening. So now when there is a clock, they will increment the max plus 1 that is neighboring. So P2, CP3, it's 8. And it will say, okay, I'm also 8. and I will increment my clock. P2 will increment its clock together with P3 to be 0. P1 see P2 and will become 4 because it sees 3, it's bigger, and it just incremented by 1. So you can see that P1 join P2, and then P2 joins P3. Well, eventually everything is done atomically, but just to explain what is happening, and then they increment by 1. So now we have 0, 0, and 4. What is important here is that the number of, in the set of clocks that we started with, the number cannot grow because we always take an existing one and add 1. So the set can only shrink or stay the same, but it cannot grow. This is an important observation. Now what will happen is that P2 and P3 will go to join P1. Sorry, only P2 will join P1, and P3 will become 1. So let's see. Because of the network topology. And then they increment by 1. Now it will be converging because P3 will see that 5 is more and join them, and then they will forever be together. Okay, so this is a simulation, and we have to prove that it's always the case. And the idea is to use a pigeonhole principle. So if you remember, I just told you that no new clock is introduced in a set, only copy plus 1. So if we take the initial clock values and put them in on the clock and use the pigeonhole principle, there should be one very big empty portion of the clocks, and this one very big is designed to be big enough. It will be shifted by 1 every time until it gets just before 0. And when you get just before 0, the clocks are incremented with no influence of the modulo. And this behaves just like unbounded case. And when they are already synchronized, they can reach 0 together, there is no problem. So this is the intuition. And we are 2 cases where if you have before 0 values are enough to synchronize the entire system, then you're fine. If not, just wait for this segment to reach before 0, and then you are synchronized. So this is more or less what is written here. So you use a pigeonhole to have a segment that is big enough, and this segment eventually reached before 0, and then you have enough time with no modulo operation implemented or used, and then the system synchronized. When they are synchronized, you don't care. They can go to 0, no problem. Apparently, there is even something that is using less states as a modulo, 2D plus 1, but then you use min. Min is sometimes is good. You go back, but so if you have clocks that are not totally synchronized, maybe you don't want to use this, you want to use the previous one. But if the pulses are synchronized, then it's perfect. It's using much less resources and memory. So instead of taking the max, we can take the min plus 1. And then in the unbounded case, of course, the min will win, and the entire system will get to be synchronized together. But in the bounded case, again, somebody can put 0 because of the modulo. Here the modulo is 2D plus 1, and there is a reason for that. If, of course, we have D pulses where the modulo is not applied, then we are synchronized. All of them get to 0 together, no problem. But if somebody put 0 during the first D first D pulses, then another, during this next D, after putting the first 0, all values in the system are less or equal D. And now, because of the choice of the modulo, which is 2D plus 1, we have another D with no application of the modulo operation, which make us synchronize when we get together to 0. So this is very elegant, using min instead of max and using less number of states. Okay, so this is some kind of a good introduction, because in self-stabilization, usually we didn't think about the possibility of some of the participants not executing the program. But this is another branch of distributed computing that was developed, in parallel, that look only on the case where some of all of them are initialized and so on, but some are acting in an adversarial way, two-faced, and try to make the system not to synchronize their clocks. So it was interesting to see, of course, there are some impossibility results that say that you have to have more than 2/3 of participants that works according to the program. This is usually the settings. There are some settings with cryptography assumption and so on that make it less, but usually it's 2/3, more than 2/3 should act correctly to overcome the 1/3 that they are malicious. And but if you tell some attacker you must not exceed 1/3 of the participant being attacked, then it doesn't seem to be something he will obey. It will use it to attack with more than 1/3 just to make the system not doing its goal, not reaching its goal. So maybe if the attacker is not always there, you want to self-stabilize after the occurrence of more than 1/3 Byzantine or adversarial participant that were maybe captured by someone that you want to eliminate its influence from the system. So, in other words, we want to recover after the occurrence of any other combination of faults, once we have only 1/3, slightly less than 1/3 Byzantine, and we want to stabilize in spite of their actions. So this will be some combination of the two communities that do Byzantine and self-stabilization, and I will show you some simple way to do it. Okay, so we assume complete communication graph, because in the case of Byzantine, if we take a ring, one Byzantine will just disconnect part of the ring if it's directed, or two will disconnect it for sure. So usually we assume complete communication graph, and then Byzantine cannot disconnect the communication among the non-Byzantine participants. And now just to make rules that simple, still we have a common pulse. So what we do, if you wish to know when to increment your clock, you just have to find enough support group. And what do you mean by support group? If, of course, the faulty processors can cheat and their number is f, you can wish to n minus f minus 1 clocks of neighbors that are identical to your own and no more. Because if you have n minus f minus 1 plus yourself, you have n minus f total with the same clock. And this is the real state that everything is working as it should. You cannot hope for more. And then you increment by one mod m. We don't want unbounded. And if you have less, then there is a question. If you have less than n minus f minus 1 neighbors with clock that are identical to your own, maybe, well, it won't, we'll see soon that it won't work, but maybe you can just do some kind of a reset and assign your clock by 0. So, of course, if we have n minus f minus 1 that are all good with the same clock, they will increment forever and they will just ignore the rest. But maybe part of the n minus f minus 1 are Byzantine that want to split between the good guys. Let me show you what I mean. But to make our life simpler, let's have an observation that says that there cannot be two, in these two rules, there cannot be two distinct clock values that are incremented simultaneously. And this is a nice observation, because if there cannot be two that are incremented simultaneously, then after one pulse, we have at most one non-zero value, clock value, and the rest are 0. So this is very nice property to have. And why this is correct? So assume we have two processors that increment, and they increment their value, and they are not 0. So each of them sees the same value as its clock. Say P1C x n minus f with x minus 1, and P2C n minus f with the value of clocks y minus 1. So together, of course, out of the n minus f can be faulty, two-faced. And they can say to x, we are with you, and to y, we are with you. So they can be counted twice. So if you look at what happened in the left, you have n minus 2f non-faulty processor with x minus 1. This is for sure after reducing the max number of faulty messages, and the same to the right with y minus 1. And now if we add them together, there are at least 2n minus 4f non-faulty processors. And this is something that contradicts our assumption about less than 1/3. So n is greater than 3f, and we get 2n minus 4f, it's greater than 2n minus n minus f, which is greater than the number of non-faulty. So we are safe, only one will be incremented. And this is very relaxing. But the other one will be maybe 0. So we can have two sets forever after the first pulse. We can have at most two sets. One of them is 0. Okay, so let's look at what is happening. Here is a simple example. The Byzantine is P4, and he is two-faced. He would like to make P1, P2, and P3 that are all good guys to stay not synchronized forever. Here they are 0, 0, 1, and he would like to leave them unsynchronized forever. So by our first rule, everyone will look for two clocks that are like its own. So if you look at P1, it can read P2, it's 0. It can read the messages from P4, it's also 0. So he assumed that the system is in a good shape, where P1, P2, and P4 are the good guys, and they have 0. So P1 has to increment its clock by 1. What about P2? P2 doesn't see enough zeros, so he will reset to 0. And P1 doesn't see enough ones, he will reset his clock to 0, too. So this is what we get. We get 0, 0, 1. Okay, now the Byzantine will change its strategy, and we let P3 find out that he should increment because this is 3 zeros, and the rest will see that not enough support set, and they will reset. And this is what we get. But this is very familiar. This is the first configuration we saw. So in some sense, there is an infinite execution that P4 is capable of enforcing, and the clocks will never be synchronized. And this is bad news, right? So how can we copy this? Of course, we cannot hope for more. When you see n minus f, you have to increment, but maybe if you are in 0, maybe you can be cautious, because you see, if you are in 0 and you are going to increment, there is a possibility that you are the only, of course, you are the only one that can increment, because in every configuration, only one value can be incremented. So 0, if it's incremented, maybe there are others that will reset to 0. So if you are someone that look from outside the system, you will tell the zeros, wait, let the other join you in 0 and then go out. And if you go out together, then you have your support system through all the values and you continue. So here we introduce randomization that will help us doing this, playing the outside observer that tells them wait. So when you are going to leave 0, you flip a coin, and then you decide whether you are going to increment or stay. And if we are lucky enough, and we don't have too many participants, maybe 4, then those that are going to leave 0 are going to stay. The ones that are non-zero will join 0 because they cannot increment, only one value can increment. And then they all leave 0 together by using another coin toss. And once they leave together to 1, then nobody can fool them anymore, because they all are good guys and they're not two-faced, and they see each other as they can continue forever. There is one issue here that we should look at, because they don't remember when they get after, maybe the clocks is 12 hours, and maybe after 11 hours they get to 0, and maybe they use randomization again. This is something that we want to avoid. So let's say that if you get to 0, not through reset, you just exit. And then once you are all in 1, then you continue forever, and getting to 0 is not an issue because you just entered this by incrementing. So here is the scenario when the randomization helps us. You see that, of course, now the only one that can increment is P3, and it can use randomization, and in this case, the randomization tell him go out. So he went out, and this didn't give us a chance to synchronize. But then then in this case, the only one that can increment is P1 because he has a support of P2 and P4. And then he uses randomization and stays. It could increment, but it stays. The rest must set to 0. Now they are all 0. Now if all of them use randomization and go to 1, that's it. From this point on, they continue and just forever are synchronized. But as I told you, there is an issue of getting from 0 and not using randomization again, because you get to 0 in an increment mode, not in a reset, so you continue. So this is the actual algorithm, and what you can see is that we have some collection of clocks. Some of them are not answered, and then we have the flag of whether we get to 0 through increment or through reset, and this change our decision whether to just increment or use a coin toss. So if you can see, if increment is false, it's different where last increment is true. And this 13 and 14 show that we do something else according to last increment. And okay. But there is still, and this is the outline of the proof. So there is one issue here, that if the clock is very big, it can be that it will take the opportunity to leave 0 together, something that is related to the M, to the size of the clock. And if M is 2 to the 64, then the synchronization or the convergence will take forever. But we'll solve it soon. But for now, let's assume it's very small, maybe 3, maybe 2. And then you have very often opportunities to collect everybody in 0 and continue to 1 together. So our scheme is saying that you need 2 to n minus f, 2 to the power of 2n minus f chances until you all get out to 1. But if n is 4 and f is 1, then it's very, and most, if you look at the cases of what is the 4 and 1 is 1/4 of faulty, and the most you can get is 1/3. So I'm not sure that it's not a good idea to start with 4 portion of the system. So this is one issue. The other issue is M, where M can be 2 to the 64. Then you have a chance to leave 1 every 2 to the 64 rounds, which is not acceptable. So what we're trying to do is we're trying to make M to be represented by small clocks. And this can be done by the Chinese remainder. So we can take a combination of primes, M1, M2, and MR, such that their combinations are 2 to the 64. So if you take 2 times 3 times 5 and so on, until to get to 2 to the 64, it's not much. It's like the log of 2 to the 64. And then we get clocks that operate in parallel, and each of them converge in relation to the M that it represents. And this is fast enough. But overall, if we take all the combination of them, we have some clock that is incremented by 1 every time. I will show you in a minute. And then we get what we need. We get a very fast convergence, which is this the idea. So you have some kind of non-carry increment. So the first digit is mode 2, the second is mode 3, the third is mode 5, and so on. And then we can map every combination to a number. And the number will be one of 2 times 3, 2 times 5, 2 times 7, which is a big enough number. And the combination never repeats itself until all these options of the multiplication of 2 times 3 times 5 times 7 are exhausted. So this is very useful way to do it. And you can see that all of them are 1 now. Now some are 2 and some are, and so on. And the combination do not repeat themselves until you exhaust all possibilities, and you can map easily these numbers to a number that is agreed by all, and it helps us in synchronize the clock very fast. I'm very fast with my talk, so if you have questions, I'm going to just conclude, but let me just tell you something that I'm proud of. So there was some computing review. Someone reported I used the entire paper a few years ago to design some middleware. The article is 19 pages long, very readable, and as mentioned above, was used to create real software. And this it's not only a game. In some sense, if you understand the concept of self-stabilization, you can understand the entire internet cannot work with if it wasn't self-stabilizing, because you cannot call some engineer to change some router and routing table. You have to make sure that everything is recovered automatically by itself. And it's not something that you have to even use detection and then correction. It can be some inherent property of the algorithm in the design. So you do it seamlessly, but it works, and it is somehow by miracle. Of course, you have to understand the notion and what should be taken care of. And if you don't have a question, I can give you some other algorithm, but please. I see Ken that please, Ken.
Well, I do have a question, and I'm sure others will have questions too. So suppose that I'm interested in very high quality real-time clock synchronization in a Ethernet distributed system or something. Can I combine these self-stabilization pulse algorithms where the clock really is a pulse? Can I combine those with some source of real time, such as GPS, and would that give me a higher degree of clock accuracy than if I didn't approach it that way?
Yeah, this paper that I'm now just referring to is also techniques to get rid of the pulse. So what we do to do it is something like we have some drift and some error in messages and so on. But still, we use randomization to get them all to have a common pulse. Once they have a more or less common pulse, we can apply the algorithm that I showed.
Very good. And so now I have a follow-up question, really. In what I do, often what we worry about are causal orderings, or I really should say potential causality, that event A communicated indirectly or directly to event B, and therefore A could have caused B. Now, there are clocks that combine real-time and causal information. Leslie Lamport had one. The more practical one tends to be a clock built by Kulkarni, that has a causal component and then it has a clock component. Have you thought a little bit about self-stabilization relative to causal information?
Yeah, I think that in some sense you can have some vector timestamps and so on as Lamport do and make it self-stabilizing. So any task that you can take, you can think about distributed, it's an opportunity to say, okay, what happened if the state space is so, and I start in some arbitrary state, let me have eventual properties, like eventual logical clocks or eventual causality, and then there is a technique called fair composition of self-stabilizing algorithm. And this technique says, okay, now you have using this clock to another self-stabilizing algorithm. You run them in parallel, one step from each. Eventually the clock stabilizes, and then the ones that rely on the clock that are stabilized start stabilizing. So you can have a hierarchy of stabilization. Each of them is proven by itself, assuming the previous one already done, already giving you some invariant or some nice property you need. So this is a fair composition of algorithms, of self-stabilizing algorithm, and it appears in the paper you mentioned that is cited a lot because it makes the life simplified. In this place, yeah.
Yeah, no, this sounds really very nice. I'm going to look at it more. In fact, I've been intending to start to use self-stabilization for bootstrapping distributed systems. So often it's hierarchical also. You would like to bootstrap to find an initial leader, then the leader can bootstrap a distributed membership protocol, and that can drive some kind of big database system or something towards a stabilized, consistent state. So very, very interesting, Shlomi. I really find this fascinating. Okay, I monopolized too many questions here. Maybe other people have questions.
But I just want to give you one comment. We don't think about it first having a leader and then. We say, do leader and do then together. So then the next one, anyway, is self-stabilizing, doesn't care about the initial state. So until the leader is elected, you do a mess with the second one. But then you started in a good, in an arbitrary configuration, you start having the invariant of the second layer and so on. So this is
yes, I see what you're saying. That's very nice.
Yeah, thank
Good.
you.
Okay, maybe somebody else has questions for Professor Dolan.
A quick question. Since we have like a closure in a loop, like basically there's feedback, there is also the possibility of resonance, I'm assuming, like where you can go destabilize, like where,
Yeah.
I mean, I'm a control engineer. Always when
Yeah. So you see, we are not interested what happened before we start the convergence.
I see.
So
period where you go like, try to settle. But I mean, there should be something to assure the loop is going to be stable. I mean, the poles are basically on the left side of the S-plane or something like this, right?
You wish to have the convergence fast enough.
I see.
So you get some, some useful work in between two arbitrary faults.
Okay.
Yeah, so this is so convergence speed is important.
And now going down that rabbit hole, like basically there will be some gains that you apply like from the feedback, and those gains basically determine like the rate of your damp, right? Like an over damp or like something. Do we have those gains constant, or we can also adjust them to have like, let's say, a smarter or faster convergence?
I'm not sure that we understand each other. I don't understand really. Maybe you can take it offline. It's
Okay, sure,
interesting
sure.
to look at it, and
For sure.
maybe we can have something to work together.
For sure, absolutely. With my
But
pleasure.
yeah, sure. So what I'm saying is overall that we really would like to have the pure vision of not caring about what happened when something wrong happened, because
Yes.
if you take in account what something wrong happened, maybe one scenario you forget, and this happens when you send the missile to the moon. This is exactly what happened.
Yeah.
So we don't want to just get any scenario, an answer for any scenario.
Yeah. Yeah.
Yeah.
Okay, do we have other questions?
So Shlomi, that was a beautiful presentation. Thank you.
Thank you very much.
I've been in love with and enjoyed all of the self-stabilization algorithms for all of my professional career. So I'm delighted to see you bring this clarity to the world. Thank you for that.
Thank you.
I haven't seen the computing reviews paper, so I'm going to print it off next, and your Dolev and Welsh Journal of the SEM paper in 2004. But what I have been trying to work on the problem that the computer science industry has different beliefs in the ontological substance of the universe than physicists have. And one of the things I did almost all of last year is to try to gently introduce this community to the idea that synchronized time actually is a fallacy. The space-time doesn't work that way. But I don't want to preach anything here. There's enough stuff on videos on me. The question I'd like to ask you is, how do you see relativity, for example, either special or general, special is enough, or quantum mechanics and indefinite causal order in the way physics works, working with your algorithm here? Or do you see it as consistent with it? You don't understand, the physics of it, and so you've derived this completely independently. So tell me your views on relativity and quantum mechanics in the relation to synchronized time.
Yeah. So, I'm fascinated about entanglement and stuff like that. I'm doing some quantum key distribution algorithms now. I play with this. And the collapse that happens simultaneously is an opportunity to think about more options on how time behaves and so on. So this is something that I think that I saw a paper on self-stabilization and quantum, and it will be interesting to explore and to see what can be done. Especially, there is also a notion of privacy, because you can change the the state of the particle that is in superposition, and if you don't collapse it, say the participant is honest, then he got no information of what's going on. And this can be very nice as a privacy and self-stabilization together, to find some way to play with the vector of them, like vector in a quantum computer. This is interesting to look at. Yeah.
So I don't want to dominate the questions either. Does anyone else have a question? And then I'll ask another one.
Shalomi, like another question came to my mind is, when we have these stabilizations, they are basically some loops, I'm assuming, right? Of like propagation of information that goes around. Is that correct? My notion on that?
Yeah, in some sense, if you stop working, then I can put you in any configuration and nothing happens.
Yes.
If you want to converge, you have to continue at least check your neighborhood that they are in a good shape. So
Yeah.
there are some kind of a class of algorithm that is called silent self-stabilization.
I see.
Let's say that you span a BFS tree, and you just look at your neighbors and you see, okay, I have a parent that is one distance smaller than mine, and my children has one more than mine. Then if we can check it, everybody check it, and nothing happen, and nothing is coming incorrect.
Yes.
So maybe you are done. You just have to check. You don't have to change.
Yes.
So there are several, notions that make it interesting, like proof labeling scheme, like local algorithms. It's really some new views that make you go to a different path and
Absolutely.
combine
Yeah.
it.
Thank you.
Excellent. That's
We
good.
are almost out of time. I think we have time for one last short question from Paul here.
Okay, so we see, I mean, I have my foot in both camps in the hardware, software implementation in large-scale companies as an engineer and also as an experimental physicist, and I am in touch with the quantum computing community. One of the things that you just described here is known as the no cloning theorem, which is you're probably aware of, is very well proven and accepted in the physics community. But there are other interesting things like superposition. Is this what a Paxos or a Raft algorithm goes into until it's decided? Is that the kind of good analogies that we can draw to try to bring these two communities together?
Yeah, maybe, I think that to make today something out of this quantum to replace Paxos, it won't be easy. We need, to do it in Amazon, in all these cloud providers. It will take some gap until we can use this technology. But of course, I think that there is an opportunity to use quantum networks. I read a paper I may send you that there are some breakthrough in quantum networks now. They do some computation.
And we're kind of aware of some of those. We're deeply connected to the quantum networks community, but the thing that we've discovered seems to be the same thing that you've discovered. You have to have triangle networks. A single Alice and Bob talking to each other basically can, if that link breaks, let's say it decays or someone cuts the cable in Ethernet, then what happens is they're going to sit there forever unless something external intervenes. And that's what causes everyone to think they have to have a timeout and a retry, which we claim is the root of all evil in distributed systems. Or, as the quantum community, the quantum networks community have discovered, you have to have triangle networks. You need at least one other neighbor, and it works better when you have 5. It works even better when you have 7. So the quantum networking community seem to be approaching this problem from the other side of the elephant, let's say.
Mm-hmm. Yeah, interesting. Computers and computer science change so fast. It's very nice. We are lucky.
Yes.
We are indeed.
Let me suggest that we thank Shlomi, and then we turn off recording, but people who want to linger and talk longer, there's no problem.
Sure.
So
Yes,
join me in giving him a hand.
applause.
Yeah, and then we'll basically proceed in 2 weeks with a talk from Ken. All right.
That's absolutely right.
We'll stop the
On the
recording.
16th, there'll be an announcement of that. Okay, but if people want to stay, I don't see a reason not to. It's just, I just thought we are timing people. We should stop after 1 hour.
Yeah.
So.
I mean, usually we go beyond. So.
Well, I can't. I have another thing I have
Sure.
to do.
Okay,
Yes,
we'll stop the
we
recording.
can also communicate offline, whoever
Yes.
wants.
Let's communicate offline. I'll put
Just for the recording. Bye, everyone.